Right, today I'm going to go through a video on running your first OpenFOAM simulation. So hopefully now you've got OpenFOAM downloaded and on your computer. I'm just going to show you in the most basic sense how to run your first simulation, how to view the results, how to view the mesh, and how to do a small bit of post-processing to check your results. I'm not going to go through detailed analysis and comparing between experiments for now. I'm going to do that in some detailed cases later. For now, it's just running your first simulation and taking a look at how OpenFOAM actually works. So firstly, if you've got OpenFOAM downloaded, you can go to where the tutorial folder is by going to cd in your Ubuntu terminal, $foam_tutorials. Okay, so here I've got all my tutorials here. So I've got compressible, I've got Lagrangian, combustion, all different types of test cases. Keep things simple. I'm just going to go to the incompressible folder and take a look at the different cases here. Actually, it showed me the solvers first. So there's a bunch of different types of solvers here. There's a simple algorithm called SimpleFOAM, PimpleFOAM, Piezo, lots of different solvers. SimpleFOAM is a steady state solver. It's the most basic solver pretty much you have. So I'm just going to go ahead and pick a tutorial case from the SimpleFOAM test case. And as you can see behind me here, there is a backwards facing step which I'm going to go through today. So listing tutorials here, you can see that the tutorial that I want is this backwards facing step 2D. So this is the case that I want. Now, just like in the previous video where I copied the cavity tutorial, I don't want to actually edit this base tutorial. I want to copy this test case to my working directory. So I'm just going to cd back to the highest root here and go to my hard drive, go to D and go to my OpenFOAM working directory. You can see I've got the old cavity test case here. So I'm going to do cp-or to copy a folder. And the folder that I want to copy was in this directory here. So user lib OpenFOAM incompressible SimpleFOAM is what I want to copy, and actually out of that directory what I want to copy, I'm just going to type it in just because I don't want to execute the command by accident. So copy user library OpenFOAM 2312 tutorials incompressible SimpleFOAM, and the case was backwards facing step. It should autofill for me when I press tab after I start typing back. So this is the folder that I want to copy, and now I have to just tell the terminal here where I want to copy it to. So to copy it to the directory that I'm currently in, I just use a full stop. So typing in that command and then pressing ls, you can see that I've now copied that test case, and I can start working in here in this directory and changing things without worrying about losing that original test case. So moving here to the backwards facing step, you can see that I've got a few files here. I've got a 0 folder, a constant folder, and a system folder. Now I'm going to copy the 0 folder and I'm going to change that name to just 0 on its own. This .org here is just to say that that's the original 0 folder. That's not meant to be changed, so I'm just going to change this to be 0. So how I'm going to do that is I'm going to copy the directory 0 and I want to paste that in the same directory I'm in, so it's going to be a full stop there after that, and I'm going to do \0 to say that I want this new name of this folder to be 0. If I press ls again, you can see that I now have that 0 directory pasted in here, and I'm going to remove this 0.original because I don't need that anymore. Okay, OpenFOAM won't run if you try run tutorial cases with the .org in front of the 0 cases. So I'm going to show you what this looks like now on my hard drive, just because it's a little bit easier to see than in the terminal. So I've got my backwards facing step, I've got 0, constant, and system. In the 0 folder, this is pretty much where you define your initial and your boundary conditions for the simulation. So I'll explain these a little bit later after I show you what actual test case we're running here. In the constant folder, this is where you define your models, mainly like if you have any chemistry, combustion models, thermodynamic models, And here we've got transport and turbulence are the models that we're using. And finally then system, this is mainly different files you use for meshing for your finite volume solution, and sometimes some post-processing functions go in here. So there are the three kind of file directories. No, it's not crazy complicated. It's maybe 15-20 files here. So we've no graphical user interface here. So we need an external software to view what we're actually doing in this simulation. So when you installed OpenFOAM, a software called Paraview should have been also downloaded. If you haven't downloaded Paraview, just go ahead and download Paraview. You can just look it up on Google and download Paraview. But we need to load up this software called Paraview to view our mesh and our boundaries before we start the simulation. Okay, so I've loaded up Paraview, and the first thing I'm going to do is I'm going to mesh the domain, and then I'm going to show you the boundaries. I'm just going to talk about what we're actually doing in this simulation here. So we're just running a simple 2D backwards facing step. This is just on the NASA website, the Langley Research Center website. All the details of the boundaries are here. Free stream inflow and a pressure outlet to get a specified Mach number. We've got a symmetry condition here at the beginning, just so that the inflow condition boundaries and the wall conditions don't conflict with one another. And then we just have adiabatic solid walls and a unit step height here for this backward facing step. And there's a few results here that we can take a look at, like the pressure coefficient and some velocity profiles once we're done the simulation. The meshing is done by OpenFOAM in a file already, so the details of how the mesh works is done in the block mesh dictionary file. We're just going to execute to construct a mesh, and we're just going to execute the simulation. We're not going to talk about meshing today. We're just going to run the simulation and look at the results. So firstly, what I'll do is I'll open this up in Paraview so we can view what's going on. It's very hard to understand what's going on in this simulation when it's just in text files. So step one here with pretty much all OpenFOAM simulations is to mesh the domain. So we're going to run this command called block mesh, and what this is going to do is this is going to run the command that tells OpenFOAM how to mesh the domain. And then what I need to do is I need to create a file that I can open in Paraview. And how you do that is you just need to create any file with the extension called .foam. Okay, so how I do that is I use the command touch. That's just going to create a file, and I'm just going to create a file called step.foam. This is our backwards facing step.foam. It could be called anything, step, banana, monkey. It does not matter what this file is called. When I'm running different cases, I'll give it a certain name, like say 10 million cell airfoil.foam, 15 million cell airfoil.foam, etc. So create this file, and now what I can do is in Paraview I can go to my working directory, backwards facing step, and just click the step.foam file and hit apply. Now this has opened up my full domain here, and if you can't see your domain, you might just have to click this little eye here just so you can see it. And what I'm going to do is I'm going to change this here to be a surface with edges so I can view the mesh. So as you can see here, we have a standard hexahedral mesh, quite stretched elements here. That's due to the boundaries that are applied over there. And the mesh is refined around this backwards facing step here. So this mesh looks okay. I'm not going to talk about how to change the mesh here today. So we're just simply inspecting the mesh. We've got quite a decent Y plus here as well. There's some details I think on the mesh on this page here. So details of the mesh are there. Okay. Now we know what the mesh looks like. We need to know what boundaries we have and what the names of these boundaries are. So you can see here in the mesh regions here, I'm showing the internal mesh. But if I want to just look at where's the inlet and the outlet in this domain, I can hide that first of all and just highlight inlet and let's say the outlet as well, and then hit apply. Okay, so you can see here's the outlet over here. It's quite a long domain, so it's kind of hard to see. And here's the inlet over here. Let's show a few more faces so it's easier to see. Lower wall. That's the lower wall of this domain here, this black solid wall, and this black solid wall here. That's that lower wall there. Also, if I do the lower wall startup, that's where that symmetry boundary condition is applied. That's out here. So you can see we're starting to piece together what each of the different boundaries are in this domain. Front and back are the front and back faces of the domain, which we don't need to see because this is a 2D simulation. Let's also just show this wall group, which is just going to be the rest of them walls there and the upper walls. Okay, so these are all the places that we're going to need to apply our boundary conditions to, such as maybe velocity, pressure, temperature, etc., things like that. And also, if we're running a turbulent simulation, which we are in this case, we're going to have to tell the solver what we're going to be doing turbulent-wise at these conditions. Is there a specified kinetic energy or dissipation rate, etc.? So that's what my domain looks like. I'm just going to highlight everything here and hit apply just so I can see everything put together. And I'm ready to go and explain what boundary conditions we're applying here, and then run the simulation to show you how we do this. So going to the 0 folder, this is where I told you we apply our boundary conditions. And first of all, I'm just going to show you the velocity folder. Okay, so this is just given the name U, and this is what comes from obviously the tutorial file that we're using right now. Firstly, we define our dimensions here. There's nothing really to change up until about this point here. And this is basically initializing the internal field of the simulation for what we want our velocity to be. So this is just like the initialization step in ANSYS or STAR. In this case, we're defining an x velocity of 1e to the minus 8 and 0 and 0 in the z and x. The reason that there's a small velocity here and it's not exactly defined as 0 is because sometimes you can get errors if you define a completely 0 velocity in the domain. Because what you're doing is you're setting the turbulent kinetic energy equal to 0 as well, which can basically cause some floating point exceptions and some errors there. The next step then is to apply the velocity at the actual different boundaries. So that's the inlet, outlet, and the walls. In this case, the inlet is just going to be a fixed velocity inlet boundary of 44.2 meters per second in the x direction. Simple enough. The outlet then is a 0 gradient boundary condition. That just basically means that the derivative of the velocity is 0 at the outlet. You'll see that will complement the pressure outlet boundary condition once we get to the pressure condition. Here at the lower wall startup and upper wall startup, we just have that symmetry condition that we talked about. At the upper and lower wall, we have this no slip condition, so we're just assigning that the velocity is 0 at the wall. And the front and back, we're just not applying any conditions here because this is just a 2D simulation. We don't need to model these front and back domains. Next, we'll talk about the pressure boundary condition, because this can be quite important because pressure and velocity are obviously coupled. So an important thing to note here when you're running your OpenFOAM simulations is it's not like ANSYS, where ANSYS wouldn't let you apply, let's say, a fixed pressure and fixed velocity at the inlet, because that doesn't make sense. You can't have the pressure and velocity both defined at one boundary, say the inlet, because that's essentially applying, if you apply a pressure and a velocity to an inlet, I believe that will be two Neumann conditions in the same place, which are maybe a Dirichlet condition. I can't remember the difference between the two. I believe it's a Dirichlet when you assign a value to a boundary. But anyway, we can't. Basically, the mathematics don't work for assigning both pressure and velocity to that same boundary. So at the inlet, whereas with the velocity case, we're assigning a value. Then what we're doing is at the pressure condition, we're saying that the gradient is 0. If I were to change this pressure to maybe, I don't know, 1 atmosphere at the inlet, I would get an error. Same with the outlet then, we're assigning a fixed value pressure condition at the outlet, whereas the velocity was 0 gradient. So that's how we're defining our conditions there. And then some very, very similar conditions here with the walls. So lower and upper wall, 0 gradient pressure, symmetry at the conditions we talked about before, and 0. So that's our velocity and our pressure fully defined. That would be our flow field defined, let's say. So the next conditions to talk about are the turbulent conditions. So in this simulation, we're actually going to be using the K omega model. So the only two other files I need here is K and omega. I just have to define what the turbulent conditions are at the inlet. In a software like ANSYS, you might have, let's say, a 5% turbulent condition, or you might define the turbulent kinetic energy value itself. In this simulation here, we're going to define a uniform kinetic energy throughout the domain to initialize the simulation, and then the kinetic energy at the inlet is a fixed value, and the value is calculated from the internal velocity field here. So really the only value we're actually putting in here is we're just assigning a fixed turbulent intensity to initialize the simulation. So this doesn't really matter too much because it just might affect your convergence, because the turbulent kinetic energy is going to be computed from the internal field anyway, after a few iterations. Outlet 0 gradient, symmetry again at the symmetry condition, and then at the walls then we're using a wall function for the turbulent kinetic energy. So you may or may not have seen that wall functions can be used to define what the kinetic energy is at the wall, just if your mesh is a little bit too coarse and can't compute what that is. So just we're using a wall function here essentially to compute this kinetic energy, and that's calculated from the internal field. It will use flow field values to compute what that kinetic energy is at the wall. Very similar stuff then with omega. Almost exactly the same, fixed value at the inlet, 0 gradient, and we're using an omega wall function to compute that turbulent value of omega there. Then uniform within the field, I believe these would have just been, this uniform value would have been calculated from this turbulence intensity that I talked about. So you can relate K and omega. For a specified turbulence intensity, you can calculate what K and omega are just through simple hand calculations. So I won't go through that because it's very simple. It's like a 3-letter equation. So that's the boundary conditions fully defined for the inlet and the outlet. Then we're just going to move on to what the specific models we're using are. So if I open up the transport models and the turbulence properties, in the turbulence properties, I'm just defining that this is a RAND simulation. And then here for the RAND model, we're using the K omega SST. You can use something different here if you want. Actually, we do have some files set up there to run this with K epsilon, with Sparta Almaris turbulence model. If you want to see what turbulence models you can use, you can actually just set this to 0 here, and then you'll get an error, and it will print to the console telling you what turbulence models are valid here. But we're going to stick with the K omega SST. Turbulence is on, and it's going to print the coefficients for us so we can have a look at them. Save that. Transport properties, we're just using a Newtonian fluid model with a specified viscosity here, so nothing really to talk about there. So that's our simulation fully defined now. Last thing is in the system folder, just to describe what time step or how we want to step through the simulation, how we want to iterate, and what solver we want to use as well, like that. So here, the 3 files we have to worry about is our control dict file. That's pretty much going to set the controls for the simulation, like how we're iterating and when we write out the simulation. And FE schemes and FE solution talk about the solver itself. So let's talk about the solver, and then I'm going to actually edit the control dict so we can start running the simulation. So this is a steady simulation. So we set the DDT sim just to steady. And then here is just different gradient schemes and also schemes for the Laplacian in the solver. So in the solver, you've got terms that are being taken a gradient of or a Laplacian from. So you're just describing how you want these terms to be computed. So Gauss linear is going to be used here. For divergence schemes then, it's just, again, very simple, bounded Gauss gradient schemes here. Nothing really to touch here. I generally don't touch this stuff when I'm running simulations. I'll use a tutorial case and I'll just kind of leave the solver settings alone. Interpolation schemes, linear interpolation, and again, we're just going to leave the basics here. There's not too much to discover here. In the solution, we just talk about the solver and the different tolerances and residual control and relaxation factors. Again, I'm just going to leave the defaults here. I would only really touch this if I were getting divergence. Maybe I'd increase relaxation or change some tolerances. And here it just describes what we need to know here for the simple algorithm, or what would you say, the parameters for the simple algorithm. So we're not going to use any non-orthogonal correctors here. If you want to, you can, but you can see our mesh is pretty orthogonal. Actually, not very much at the end, but we're going to, again, just stick with these default settings. We're using a consistent algorithm. So actually, in this case, we're using the Simplec algorithm. So it would look like this if you were to see it in a textbook, but how it's run in OpenFOAM is you just say consistent yes or no. And we have some sort of controls here for residuals and also relaxation factors. Again, stick with the basics. I'm just going to leave them alone. And finally, the control dict file says what solver we want to use. We're using SimpleFOAM, when we want to start, when we want to end. So this is number of iterations. This is how often you want to write the simulation. So this says it wants to write it every 100 time steps. And purge write is basically saying here for the first 100 files to be written here, we just want to ignore them and leave them alone. We don't care what they are, because the solver will be still developing the flow. I'm actually going to change that to 0 because what I want to show you is just how the flow develops as the iterations progress. And I'm pretty much going to leave everything else here to be the basics. So there's all the files that you need to define an OpenFOAM simulation. It will be different from solver to solver. So if you're using the piezo algorithm, it'll be a little bit different. The pimple algorithm, it'll be a little bit different. And also maybe if you're using a different solver for heat transfer or combustion, you would also need some extra files at the boundary like temperature, mass fractions and stuff like that. But enough blabbing, I'm just going to run the simulation now. So running a simulation is really not very complicated. I just type the name of the solver and click enter, and it's starting to run here for me. So it's going to print out here different residuals and stuff like that. You can write them to a file if you really want to, so you can take a closer look at what's going on during the simulation. But it's okay for me. I'm just going to print the result of the simulation every 100 iterations, and then I'm going to view the results in Paraview here. So I'm just going to pause and let this run for a few minutes, and then I'll come back and show you what's going on in Paraview. Alright, so my simulation is done running here. I've got all my different files here from 100 to 2000 iterations all printed out. And you'll see that in each of these files, it's just printing all the different values that I need. So the U field, the P field, the K field, and also some extra fields that are being printed because of the functions that were just set up beforehand. I'm not going to worry about them too much. We're not going to look at them because I'm not going to do a detailed analysis here. But let's just go ahead and see how to have a look at these results in Paraview. So since I've already got this file open, I just go ahead and click refresh. But you need to open basically this .foam file that is in your working directory. So I'm just going to refresh here, see if this opens up here for me. I might have to restart it. So and just hit apply, and that's going to work there for me. So just some little errors with Paraview, but you need to be able to click that apply button for this to fully update here. So you can see here that now I've got all my different directories here basically printed out. I'm going to use the 0 directory as well because I want to show you what the simulation was initialized to. And I'll show you an animation of the simulation progressing. So how you view your results in Paraview is we're just going to click here, and you can see all the different fields being printed out here. I believe that these dots here is basically the interpolated field or a scalar field, and that these cubes are vector fields. But I haven't quite figured that out yet. But I'm just going to go ahead and look at this U field here. I'm going to change this back to surface just because it's a little bit easier to see. So this was the U field as it was first initialized. And let's go ahead and click play. And you can see that basically as the simulation progressed, how can I skip this? As the simulation progressed, our flow field started to develop. So velocity was pretty much 0. Then our velocity basically developed from the inlet. And we got our simulation to converge to what we would expect. Okay, so you can see as I move on, the simulation is not really changing that much more, and that's our backwards facing step. If you want to change the color of this graph, I like to change the color here just because I think it looks a lot better with other colors. You click this folder here with the little lover on it. Change this preset to all so you can have a look at it, and I like to use this one here, the blue to red rainbow, just because that's the default in most simulation softwares, and it's very easy to see. I don't really like that cool to warm color profile. Okay, so that's how we're going to view our results here. We can rotate around, we can look at all the fields and take a look at what's going on. So that's your velocity field. Let's take a look at the pressure. Again, pressure, there's the pressure, there's not really too much more to say. You can also take a look at your turbulent viscosity here. And we can also look at K and omega, because we did use this K omega model. Okay. And now I'm just going to show you how to plot a few results and how to compare it, basically. Okay. So let's go back to, let's just leave the velocity here, just like that. And we're on our latest time, we'll just leave it there. Sorry, one more thing I will show you is how to take a look at the streamlines here, because I think this looks quite nice. If you change this to surface LIC, you should see the, not surface with edges, surface LIC, not sure why that's not working for me. Alright, so it's getting some weird errors with the surface LIC there, so I just deleted the .foam file and just reopened it again. And I'm not sure why that was. But basically, this surface LIC here is what we can use to take a look at the streamlines. Okay, so let's put this to the latest time. Change this to velocity. I'm going to change the color profile again, and then I'm going to take a look at the streamlines, and I'm going to show you how to make it just look a little bit nicer. So change this to all. I think this is the one that I like. And let's change this to surface LIC. Okay, so you can see that it puts the streamlines in here now, so you can actually see this here. Just as a note, it's not exactly the streamlines. I believe this is line interval contours or something. I'm not sure. I looked it up earlier on, but it's in general it's representing the streamlines of the flow. You can see that there's a vortex on the bottom here, another vortex here, which you might be able to compare with people in the literature for this case. If you really want to take a look at the results of this, you could look up this case here and compare it with the authors and people who've done analysis on this. I'm just going to show you how to make this look a little bit nicer. If you scroll down here, we're just going to change the details on this LIC to make it look a little bit nicer. So there should be something on the color here for LIC. So color mode here, you could change that to multiply if you want. I don't really like the look of that, so I will leave that to blend. Enhanced contrast, I believe, and LIC intensity. This is what I was changing, and it looked better for me a while ago. So if I change this LIC intensity down, so that pretty much gets rid of it. Let's move it up slightly and see how that looks. Okay, you can start to see that it's less dark now, so I like that a little bit better, so I can actually see the velocity field. I think 0.4, that looks quite good, where I can kind of see these streamlines and I can see that vortex but still see the velocity underneath it. So you could take a screenshot, or you could do what you like there to post-process further. Alright, one more thing I'm going to do is I'm just going to plot over a line just so we can compare with some experimental results, or at least results from the literature, to get a general idea of whether we're representing the physics correctly. So the first thing we're going to do is we're just going to plot the pressure coefficient on the lower wall. So the lower wall was this guy down here, just at the very bottom. So what I'll do is I'll just plot the pressure coefficient on the lower wall just to show you what that looks like as a field, and then we'll get a graph of what that looks like. So the pressure coefficient on the lower wall would look like this, and I'm going to go up here to filters, search, plots data, and I'm going to click this window here. Well, let me just first click apply, and then I'll show you how to break it into windows. Hit apply to plot data. Now it's plotting all the data points for me on this lower wall. I'm just going to select all and then turn that off. Right, now let's just plot the pressure coefficient on that wall. And actually on the x-axis here, we've got an array. I'm going to use the x points here. So this is just the actual x coordinate, if you will. I believe we're off by a factor of 10 or something, because this is all done non-dimensionally, and the graph here is in millimeters, so I think we're off here by a factor of 10 or 100, but we'll adjust the axis to look properly here. So to compare the results we have with the graph here, I'm going to plot the results between I believe it was minus, let's change this back to points x. I'm going to change the lower x-axis to be the same coordinates as the graph on the NASA site. So that would be the bottom axis. Bottom axis range, let's change this to, it's basically this region in here, which looks like minus, let's say 0.05 to 0.3 here. That's representative of 5 to 30 millimeters, if you will. We're off by a factor here, if you will. And you can see here that after the 0 point, we do get this sort of drop in the pressure, or in the pressure coefficient, I should say. And this pressure coefficient hits a lowest of about 0.23, then it rises up again, and then we hit a highest of about 0.36 or so. And you can see from the graph we have the same shape here, and not predicting it as exactly as this here, because obviously we probably have a different turbulent model and mesh and setup, etc. So it's about minus 0.18, 0.19 for NASA here, and 0.04 I would say there. So we're close enough, definitely in shape, and magnitude's a little bit off. So if I wanted to improve this, I would change the probably turbulence model, mesh a little bit finer, and make the mesh more orthogonal, is what I would do. You can also see there that from the ANSYS, from the OpenFOAM website, when they ran this case, they got kind of similar results to us here, where they got about maybe 0.23 and about 0.39 or 4 here. So very similar results to what we're getting with this simple foam. So we know we've run everything okay here with the pressure coefficient. One more thing I'll show you how to do is how to plot the velocity over a line. So how we're going to do that is we're going to use the plot over line tool, and we're going to plot the velocity at this x over h equals -4 location. That's a vertical line if I'm looking into the domain. So let's go back to our .foam file and show the internal mesh here. And I'm going to go back to the velocity this time because it's the velocity I'm worried about. Hit apply, and the x over h equal to -4 will be a vertical line just behind the step here. Okay, if you want to see where that is, you can scroll down here and turn on the axis, and we can take a look at what that looks like. So axis grid should be here, data axis grid, and you can see that we can now see where that is. So this 4 millimeter point is going to be just here, a vertical line just there. Okay, so let's go ahead and plot that line. So filters, plot, type in plot, and we're going to do plot over line. Not sure why it's not letting me do that. I think I need to update something. Maybe click refresh. I might have to do this on a clipped plane. Let's delete this for now. Okay, so I think I was still in the other plot, which was kind of disrupting me. Plot over line is also here, just in case if you want to do it from here. So plot over line, the line we want is a vertical line at 0.04. So that's going to be x coordinate and minus 0.04. We should see a line start appearing for us here. Yep, that's that point there. And then here's the x and the y, or sorry, the y and the z coordinates. We're going to leave them as 0. Actually, we want the y to be a little bit lower here, so we're getting the full domain. So let's do maybe minus 0.1 on the y, just to make sure that we're fully getting the domain in. Yeah, so that's just, I'm just basically creating a line that's going to extend past the domain at both ends, and we'll do 0.1 on the y here. We'll do minus 0.04 here and 0 in the z, and you can see that I have this sort of straight line here now, which should be capturing this full domain here. Okay, actually can't see the end of the line. Maybe we'll have to increase that y a little bit more because I'm not sure if that's capturing the full domain. Yeah, so I just had to increase that to 0.2 because you can see the end of the vector is here. It wasn't fully going through the domain. So I hit apply, and that now plots that line. And I can show that by just clicking this little eye here. You might have to click one of these here to create a new window to actually view your plot. So if you ever exit out of the plot and you want to see this, what's going on, what you have to do is, you can see that I'm clicking show my plot and it's not showing here. So how I would do that is I need to split my view here, click on the new view, and then press the little eye and it'll pop up for you. Alright, I don't care about anything else except the velocity. So let's do, is it the U magnitude we want to compare? This plots U over U reference. I believe that's the X velocity versus the Y. So what we're going to plot here is, I'm actually going to plot on the y-axis. I'm going to plot the y coordinate. So that should be points y. And on the x coordinate, I'm going to plot the x velocity. Okay, and you see I get this profile here, and that is quite similar to what we have here. We need to change the again the extent of the y domain so we can compare with this graph fairly. So the y axis, or in other words the left axis here, we're going to change it to be this 0.05 as that's equivalent to the 5 millimeters that they've cut off there. So let's change this left axis, if we can find it, to be 0.05 as the max. Yeah, so 0.05. And you can see that I have quite a similar shape here to what was shown in this graph here. And the U is non-dimensionalized by the reference velocity. So I believe the inlet velocity here was 40 something. So 44.2. So U over U ref is going to be equal to 1 when we're at 44. So when we're at 44, this is U over U ref equal to 1. And you can see that, or maybe they're taking a different reference velocity. They must be if we're not getting a matching graph there. They must have taken this reference velocity to be, yeah, no, well, that's right, yeah, about. So they're using this max velocity as the reference velocity and normalizing it so that the graph ends at 1 there. So I'm happy that the shape and the magnitude and the quantitative information here is matching what's on the NASA website. So I basically can confirm that my simulation is working well. So what you can do then is after you get that test case running, you can then change the turbulence model and run it again. What I would recommend is maybe you could copy this file. So you could copy this and change it to backward facing step to the, maybe we'll call this K omega SST. And let's create the other case as, I'm going to delete the results because I don't need them anymore because I'm going to be overriding it with a different case. And maybe in the next case, you can run it with a different velocity, with a different turbulence model. Let's change the turbulence model here. So that's going to be in constant turbulence properties. And you could try K epsilon here because the epsilon conditions are defined in this tutorial case. There's an epsilon file here, so K and epsilon are defined at the boundaries. You will be able to run that case if you want to. Just note if you're using a turbulence model that's not fully defined in them boundaries, you will probably get an error, but it will tell you in the terminal that turbulence model is not valid. Okay, so if you wanted, you could again run that case. You could compare the results between the K epsilon and the K omega SST, and that's pretty much our first simulation in OpenFOAM. And in the next few videos, I'm going to be showing you how to do your own simulation setup. So, for example, if I create a mesh, how can I then import that into OpenFOAM and run a simulation? I'm going to do a lot of my meshing in external software like in ANSYS Fluent. Because you can do that for free. If you have the student version, you can just mesh your domain in either SpaceClaim or in Design Modeler, and then you can bring it into OpenFOAM and then define the boundaries and move on. So in the next few videos, I'm going to be showing you how to run your own test case in OpenFOAM for your a random geometry that you've maybe created yourself and maybe your own mesh. And I'm going to show you how to define the boundaries and do a proper detailed analysis of the results then in Paraview. So hopefully you enjoyed. Leave me a comment and let me know what test cases you would like to run next. I'm thinking of doing some airfoil stuff, also some stuff on combustion, because that is where my research lies. So again, leave me a comment and let me know. And yeah, I'll see you in the next one.